Good day everyone, especially to you sir. For today's video, I'll be discussing to you the chapter 7, the confidence interval for the mean when sigma or population standard deviation is known, and confidence interval for the mean when sigma is unknown. But before we go through to our solving, let us first know the following terms and with their definitions in order for us to understand between population standard deviation known and unknown. To begin with, a point estimate is a specific numerical value estimate of a parameter. The base point estimate of the population mean is the sample mean x bar. There are three properties of a good estimator. The estimator should be an unbiased estimator, that is, the expected value or the mean of the estimator obtained from the samples of a given size is equal to the parameter being estimated. The estimator should be consistent for a consistent estimator. Any sample size increases, the value of the estimator approaches the value of the parameter estimated. The estimator should be a relatively efficient estimator, that is, of all the statistics that can be used to estimate a parameter, the relatively efficient estimator has the smallest variance. An interval estimate of a parameter is an interval or a range of value used to estimate the parameter. This estimate may not contain the value of the parameter being estimated. Confidence interval. Confidence interval is a specific interval estimate of a parameter determined by using data obtained from a sample and by the specific confidence level of the estimate. Confidence level. Confidence level of an interval estimate of a parameter is the probability that the interval estimate will contain the parameter, assuming that a large number of samples are selected to that the estimation process or the parameter is repeated. Now let's take a look at an example confidence level of per population mean as population standard deviation or sigma is known. Confidence interval of a population mean when sigma is known. A confidence interval constructed from sample data is a range of values that is likely include the population parameter at some specified level. Confidence interval for population mean is determined by taking the sample x bar, as you can see in the left part of the screen of your cell phone or your screen there. The x bar is the point estimate, and subtracting or adding the margin of error E, so that letter E. So if the population standard deviation is known, the margin of error is determined by Z alpha over 2 times sigma divided by square root of n. Just focus on the left side. As you can see, x bar, that is the point estimate, and the margin of error E is determined by Z alpha over 2 times sigma divided by square root of n, where alpha or that letter A, alpha is the significance level, that is 1 minus the confidence level. Correspondingly, the confidence level is 1 minus alpha. So alpha is equals to 1 minus confidence level, and correspondingly the confidence level is 1 minus alpha. So here, if we have a confidence level of 95%, so we will have alpha is equals to 1 minus 0.95 is equals to 0.05. So there you have Z alpha over 2. Here is a single value called critical value. Can be found in the normal table. When constructing a 95% of confidence interval, for example, the confidence level 0.95 is in the middle of the distribution. So look at the chart example, the diagram. The 0.95 is in the middle of the distribution, and the remaining 0.05 alpha is divided equally into two tails, which resulted to 0.025. So since you have the alpha 0.025, then divide it into two tails or divided by 2, so you will have 0.025 each. For the first cumulative standard normal deviation, 0.025 is in the left tail, corresponds to value of negative 1.96. Okay, here it is. So I think we have done the Z table in the chapter 6, which was reported by James Cabales. So if I'm not mistaken, so in the list of cumulative standard normal table, 0.025 in the left tail corresponds to Z value of negative 1.96, and due to symmetry, it will become 1.96 to the right tail. To the right, so the Z critical value corresponds to 95% confidence level, which derived as Z.025 is 1.96. So for us to know deeper, so let us have an example here. Example 1. Scores on an exam are normally distributed with a population standard deviation of 5.6. A random sample of 40 scores on the exam has a mean of 32. Estimate the population mean with 80% confidence. So since we have the data given by the examples, so sample mean we have the 32, n is equals to 40, and our population standard deviation is 5.6. So we are about to estimate the population mean with 80% confidence. The mean of error E is equals to Z alpha over 2 times sigma over square root of n. So since you have the corresponding value, so you have to substitute Z alpha over 2 times 5.6 over the square root of n. Now we need to find the critical value of 80% confidence level. For the 80% confidence level interval, alpha is equals to 1 minus 0.8 is equals to 0.2. So therefore, we have 0.1 in each tail because alpha is divided by 2, and you have alpha 0.02, so divided by 2, then you will get 0.1 in each tail. So here it is. So looking in the normal table, we find the closest value to be 0.1003. So look at the table. 0.1003, which corresponds to z-score of negative 1.28. Okay, negative 1.28 in the lower tail, and because of the symmetry, it will become 1.28 for the upper tail or the right tail. So the z critical value for 80% confidence level is 1.28. The margin of error is therefore E is equals to Z alpha over 2 times sigma over the square root of n. So you will have 1.28 times 5.6 divided by the square root of n, then you will get 1.13. So for the lower limit, you will have 32 minus 1.13 is equals to 30.87, and the upper limit you will get 32 plus 1.13 is equals to 33.13. So to interpret this, we say we are 80% confident that the population mean score is between 80.87 and 33.13. So let's move on to the chapter 7.2, dash 2, confidence interval for the mean when sigma is known. So earlier we have discussed about the confidence interval when sigma is known. Now let's talk an example about confidence interval when sigma is unknown. So for sigma unknown cases, we use sample standard deviation S to estimate sigma. We will also use the probability distribution called T distribution instead of Z distribution. This T distribution accounts for sample of smaller size, and when sample are used to estimate population standard deviation. This area under T distribution look very similar to Z distribution. To read under a curve using t-table, we will need two values. We have the degrees of freedom and the upper tail area under the curve alpha divided by half or divided by 2. The degree of freedom is calculated based on the information used to calculate S, sample standard deviation. To calculate the degrees of freedom is simply n minus 1. So look at it, the red arrow. N minus 1, and for the secant value, you will need is alpha divided by half. Remember that alpha is level of confidence, which is 1 minus level of confidence. Alpha is level of significance, which is 1 minus level of confidence. Now let's take a look at confidence interval when sigma is known and sigma is unknown differ. We learned that in sigma and interval estimation for sigma known, we use this formula x bar plus n minus z alpha over 2 times sigma over the square root of n. Now, if we look for a formula for sigma is unknown, it's very similar to the formula above. First of all, since we are using the formula in the case of sigma is unknown, then we will need to use S instead of sigma. And since we are estimating using sigma, we will need to look values in the t-table so that we have T instead of Z in the formula. Let's say we want to, let's have an example. Let's say we have to draw a 90% confidence interval on the true upper grade, a population of students taking in a statistics exam. Assume we don't know the sigma, the population standard deviation. So we take a sample n. We take a sample n is equals to 20 and sample average of 75 and sample standard deviation of 15. Since we are drawing a 90% confidence interval, the significance of level is equals to 1 minus 0.9. Am I right? So 1 minus 0.9 is equals to 0.10 or 0.10, and alpha is divided by half is equals to 0.05. Then the degrees of freedom, since we know how to get the degrees of freedom, it's n minus 1, so you will have 20 minus 19 is equal 20 minus 1 rather is equals to 19. So in the t-table, it's easy to look. In the t-table, it's easy to look the value as long as you have the degrees of freedom, you have the alpha, and in this case, in this example, you will get 1 for the 90% confidence, and you have the degrees of freedom of 19 and the alpha of 0.05, then you will get a 1.729. So now we are ready to calculate the confidence interval estimate for the mean using the formula x bar plus and minus t alpha over 2 times sigma over the square root of n. S over times s over the square root of n. Then we get 75. Okay, I'm so sorry. We will get 75 plus or minus 1.729 times 15 over the square root of n, square root of 20 rather, which will give us 75 plus and minus 5.7992, and that give us 90% confidence interval on the mean of between 69.2008 and 80.772. So it's an error there. It's 80.772. It's not 80.7992. I used to copy the point of the pi. So I'm so sorry. It is 80.772. So marking this from the distribution, we can see visually that the lower limit is around 69.2 and the upper limit is 80.8. This 80.8. This represents an interval within which we are 90% confident that the true mean exists. Remember that we do not know the true mean, what true mean is. This represents interval within which we can be certain confident. In this case, 90% confident that the true mean is located somewhere within this interval. The tail areas represent the error that is 10% chance that the true mean is outside this interval, and half of that error will be on the upper tail above 80.8, and half of that error will be on the lower tail area below 69.2. So I think that should be all for the chapter 7, which is the confidence interval when sigma is known and confidence interval when sigma is unknown.